I'm going to present our work on building a formal framework for end-to-end DNS resolution. I'm Huayi, co-first author of this paper. This is joint work with Si, Lucas, Marco, Yodok, David, and Adrian. DNS name resolution is often believed to be a simple process. Here's a textbook example. Upon receiving a client request, which is shown in green, a recursive resolver will do some work and respond with an answer shown in blue. Specifically, the resolver asks a hierarchy of name servers, first getting referrals from the root and the top-level domain servers, and then obtains a final answer from the authoritative server. But in reality, the process is much more involved. Let's continue the example. Here, each server is identified by a name. We ignore the client and the root server. In step 1, if the resolver doesn't know the IP address of the referred server NS1 to be.net, it must resolve the name with additional queries in steps 2 and 3, starting again from the top-level domain. Only after that can the resolver ask server NS1 to be.net for the final answer. This process can be recursive. For example, if the address of server NS2 to SIGCOMM' is unknown in step 2, the resolver has to send even more additional queries. Also, a response can contain multiple NS records, and then the resolver has to decide which server to ask. This is a form of non-determinism in DNS. Another essential aspect of DNS is caching. This is a big topic with many factors to consider: data freshness, negative caching, concurrency, and etc. One subtle issue here is how a resolver handles data with different credibility levels. In a DNS message, data in the answer section is considered trustworthy, but data in the additional section is not. A resolver must decide which data to accept and whether to overwrite data in the cache. What we have seen is just the tip of the iceberg. There have been over 300 DNS-related RFCs today, and this is still growing. Moreover, DNS features are not orthogonal to each other. Introducing a new feature may affect many parts of the system in unexpected ways. With all this complexity, it's unsurprising that DNS is very hard to get right, especially in large-scale deployments. There are frequent outages caused by minor misconfigurations, like this example shows. What's even more concerning is that a flurry of DNS vulnerabilities were discovered recently. They can break the system in really subtle ways. In fact, many DNS bugs are detected only during runtime, and many vulnerabilities are found by ad hoc analysis, sometimes even by chance. We argue that this break-and-fix circle is not ideal. What we need is a principled approach that can proactively and exhaustively identify problems, preferably in an automated way. And most importantly, this has to be done over a mathematically precise model, because DNS protocols are specified in human language, with a lot of ambiguities, contradicting statements, and under-specifications that can lead to crackness or security issues. This motivates us to create a formal framework for DNS. We choose Maude as our modeling language because it supports rewriting logic, which is very expressive to model a distributed and concurrent system with stateful computation. There's also a logic ecosystem around Maude with a bunch of tools for different formal analysis. Our DNS semantics covers end-to-end name resolution between client, recursor, and name servers. We have formalized all major RFCs that specify the resolution algorithm and its refinements, up to the latest changes required for query name minimization. In comparison, the privileged and the only formal model, GROOT, has quite limited coverage, especially in that it abstracts away many essential stateful operations of the resolver, including caching. From a very high level, we model DNS as a labeled transition system, where different actors maintain their local state and act upon messages exchanged between each other. A system state consists of all actors and messages, and the system dynamics is specified by a set of rewriting rules. Our model has two variants for different types of formal analysis, which will be discussed shortly. We have tried to resolve any RFC ambiguities encountered in our formalization. For example, a resolver should choose only one execution path for a given response, even though the response matches multiple cases according to RFC. On the other hand, if there is no clear way to resolve an ambiguity, we make it configurable in our model so that we can analyze different interpretations of the specs. One example here is that the minimal credibility levels for resolver to rank data, as mentioned earlier. We have actually provided many such options to make our semantics highly configurable, and here's only a partial list of them. The simplest analysis we can do with our framework is simulation, where we use the built-in simulator of Maude to run a single execution of our semantics with an initial state, which contains active configurations of files and a client request. Simulation allows sanity checks of our semantics, for example, whether it can pass standard DNS test cases. And in this sense, our semantics can be regarded as a reference implementation of DNS specs. A more useful type of formal analysis is model checking, which explores all execution paths for a given initial state. For this, we can again use Maude's built-in model checker, and the properties to check here are generally qualitative. For example, whether a given zone configuration is RFC compliant. This includes checking misconfigurations like lambda negation or secret dependency. We have predefined a library of properties, including all those supported by Groot. But there's a catch. A property is just verified on a single client request encoded in an initial state. This is not really interesting, right? Because we don't know whether the property holds for numerous other queries as well. Our solution is to introduce a generator component that automatically creates different initial states, which allows the model checker to non-deterministically explore the initial state space. Yet, it's still intractable to exhaustively search the entire query space. So the next step is to define a notion of query equivalence class such that all queries in one class have identical resolution results. Now for each class, it suffices to analyze one simple query to obtain guarantees for all. One caveat here is that we must come up with a rigorous notion of equivalence, right? And so far we have applied the notion proposed by Groot, even though it's unsound with respect to our model. And this is something we're still working on. With this approach, we can now verify properties that hold for all queries up to an equivalence class notion. Next, with the probabilistic variance of our model, we can do statistical verification, for example, with the p-VESTA statistical model checker. The properties of interest here are usually quantitative, so we can answer questions like, with a certain statistical confidence, what is the probability that a property holds? Here's an example. We analyze the query success ratio of a alleged client where when DNS servers are under a denial of service attacks. With a typical confidence level, the verifier reports that 71% of client requests can still be answered. If we double the attack intensity, the ratio decreases to 52%. And if we switch on mitigation option in our model, the success ratio increases as expected. So our framework can actually help developers and operators quickly assess the resilience of their DNS systems and make informed decisions. We've also applied our framework to analyze amplification vulnerabilities, where a single client request can trigger a large number of queries sent by a vulnerable resolver. The idea here is to run our DNS model with randomized zone configuration and client requests, while monitoring the resulting amplification factor. If it goes beyond a certain threshold, we manually analyze a suspicious initial state. And our randomized generation algorithm can be tuned towards different zone structures to allow efficient search of suspicious cases. With this approach, we have rediscovered all major non-vulnerabilities of this kind. We have also discovered several new vulnerabilities that can result in pretty high amplification factors up to several hundreds by exploiting the interaction between different DNS features like the rewrite of NS names. We also confirmed these vulnerabilities in popular DNS implementations, including bind, unbound, and apart DNS. As can be seen from the plots, where y-axis means amplification factor and x-axis means attack parameter. Our model's results shown as lines are almost always consistent with the results measured on real software shown as markers. This demonstrates the precision and the predictive power of our model. To wrap up, we have made a step in establishing a formal foundation for DNS, where we provided the most comprehensive semantics and the most versatile formal analysis today, as well as a set of tools for automation. We invite you to try this project on your own. There's much more to do, of course. For example, adding more DNS features to our formal model and more theoretical research on equivalence class for state space reduction. I'm stopping here. Thank you for your attention. We're happy to take any questions.